Cool. Hi, everyone. Welcome to the first review session for the second 107 midterm. Can everyone hear me okay? Cool. I'm Travis. Today we're going to talk about bitwise operators, floating point numbers, and I'm going to review integers to get started because they will be relevant for the part on bitwise operators. All right, so let's get started. First, we're going to talk about integers, and also Palace cats will be throughout the slideshow just to keep people engaged. So there's our first cat for the day. Okay, so integers should be no problem because you've already seen them before, but just as a review, on myth, we have like the character is the smallest integer type. It's 1 byte. Short is 2 bytes, so 16 bits. Int is 4 bytes, and long is 8 bytes. And all integers are signed by default unless your code says otherwise. So if you say just char and not unsigned char, then the compiler assumes you want a signed number. And when you assign an integer into a smaller container, you truncate the highest order bits. So if I have an integer, as an example, like let's say I have the integer ff0000e5, right? Or sorry, I'm going to make this an int. And I want to assign this into a character container. So I'm going to say char c equals a. So what will be the value of character c after the assignment? Oh, this is a 5. Okay, so you think it's 5. How many? So this one? Yeah, E5. Okay, so after this assignment, c will equal E5. So this is hex. Okay, so that's good. So we only keep the lowest order bits up until the size of the container we're assigning into, and the high order part is truncated. It's just thrown away. So no matter what integer types you're assigning, you always just chop off the left part that doesn't fit into the container. Okay, does that make sense? Any questions on truncation? Okay, so let's go on. Remember that signed and unsigned integers in C are stored in 2's complement format. So each bit in the integer represents a power of 2. Yeah?
Sorry, why is it EF and not E5?
Oh, I wrote EF because I was looking at the beginning of the number. This is E5, sorry. Yeah, there's no magic there. Thank you. Okay, so each bit in the integer container represents a power of 2, like the columns in decimal represent powers of 10. And moving from the left, you have the highest order, highest value bits, and on the right, you have the lowest value bits. And in a signed integer, the only difference between signed and unsigned numbers in 2's complement is that the first column is worth a negative power of 2. So in this case, I'm showing a character a that equals -3, and you can see that basically to get to -3, we have this big -128 in the first column, and then we add positive values to the -128 until we get back to the number -3. So if we wanted the most negative character, we would write a 1 here and then zeros in all the other columns because we don't want to make it any less negative. So that's why the signed numbers. So let's say we want to write the minimum character we can get. So all right, char min equals, so I want to turn on the left bit and none of the other bits, right? So here I would have, the binary pattern would be 1, 0, 0, 0, and then more zeros over here. So if I want to convert this into hex, I just read the bits in groups of 4. So this is the number 0 on the right. And right here we have basically 8 plus all zeros, so we have 0x80. So this hex pattern basically represents our binary pattern here. And this is a little confusing because I'm writing the bit pattern, and when I assign it into a character, it's going to become a negative number. But this achieves the same thing as writing -128 because of the fact that our character is signed. Does that make sense? So this is just using the fact that in signed integers, the most significant column is worth a large negative power of 2. Okay, so does anyone want me to go over more about how I got that value, or are we okay there? Okay, so let's talk about coming up with new, like writing numbers in 2's complement. This algorithm that I've written down here is just ultra formal, and it's a way to encode what you are already probably doing when you write decimal numbers as binary, but I thought I'd write it down just in case anyone was wondering if there was like a formal procedure. So let's say we wanted to write the number -5 in 2's complement. And let's say we want to put it into a character container. So I want to do like char c is -5. Okay, so the first step, yeah. Can
you write a little bit bigger?
Sure. All right. Giant. Char c is -5. Okay, so the first step here is to write the positive version of this number, because writing negative numbers kind of sucks. So first I'm going to write 5, and then I'm going to use the rule to make it a negative number. So I'm going to start from the left-hand side of the character, and so we have 8 bits to work with, right? I'll just set them all to 0 first. Okay, so we want to end up with the number 5. And remember, the value of each column is just a power of 2 based on where it is. So this is the 2 to the 0s column. This is the 2 to the 1s column. And then over here, we have the 2 to the 7th column. Okay, so if I want to write the number 5, I'm going to start on the left. This is 128, by the way. So I'm going to start on the left and just move to the right until one of these bits fits inside the number that I'm aiming for. So this is 128. We have 0 of those. 64, there's none of those. 32, that doesn't fit. Then we have 16, 8, and over here we have 4. So 4 fits into 5, so I'm going to put a 1 here. And now I have 1 left over to make the number 5, right? So finally, I need to add a 1 in the 2 to the 0s column. So this is the number 5. And then I originally asked for the number -5, right? So I'm going to use this trick to invert 2's complement numbers. I have an integer n, and I want the bit pattern of -n. So all I need to do is invert the bits and then add 1. So this number becomes a bunch of 1s. 0, 1, 0. Okay, and this makes sense because we want it to be negative, right? As a sanity check, the first bit should be on. And then I need to add 1. So this plus 1 will give me the final result. Yeah. All right, so this is the number -5. And as we can also sanity check this, because we know the number -1 is all 1s, right? And then I have a 0 in the 4 column, right? This is 2 squared. So -1 minus 4 gives me -5. So that's just like a check to make sure that we didn't mess up the conversion there. So any questions about writing a decimal number in 2's complement? Okay, cool. So that concludes the integer part. That was just review. If you all have any more questions about those, you can post them on Piazza. So now we're going to talk about bitwise operators, which is the new part for this midterm. We have our confused cat here. So the bitwise operators, just to recap the different types, the AND operator basically checks, when you perform bitwise operations between 2 numbers, then you'll go bit by bit and apply the operator to each pair of bits. And the AND operator takes in 2 bits, A and B, and if they're both on, like if they're both true, then the output will be true. So you use the AND operator for, you commonly use it for turning on bits in a bit vector, and I'll go over that a little bit later. The OR operator, just as a reminder, has the semantics such that if A or B, like if either bit in the input numbers is true, then the output will be true. And both bits could be on, and it would still, the output would still be true in that case. So OR is like either input or both inputs are turned on, then the output will be turned on. And, oh, sorry, I misspoke earlier. So the OR is for turning on bits in a bit vector, and AND is commonly used for masking off bits. All right, and then we have XOR this one's rarer, but basically the semantics here are you take the meaning of or and then you say I actually don't want both to be true. So A or B is true, but now the difference between or and XOR is that we don't want both bits to be true. So this one is not, you can use it for finding differences between two numbers. Sometimes it's used in fancy arithmetic optimizations, but usually it's used in tricky CS107 questions. And then down here we have the unary operators that just take one input. So there's the familiar not, which just inverts all the bits. And then we have shift right and shift left. So shift right will just basically move each bit to the right by whatever the number of places you specify after the operator. And this has the effect of dividing the number by 2 for every place you move it to the right. And the type of shift depends on whether the number is signed. And I'm going to go over that in the next slide. So we'll cover that in more detail. And then there's shift left, which basically does the opposite. You're going to move each bit to the left, the number of places you specify after the operator. And this has the effect of multiplying the number by 2 for every column that you shift it to the left. And when you shift, you have to throw away the bits that are being pushed off the end of the number. And the question is what bits you fill the new empty space with. So just to give you an intuition about why shifting is the same as dividing by 2, I can just write another example bit pattern here. So let's say I have the number, oh, I need to write bigger, sorry. So I'm going to use character again because it's easy to write on the board. But I'll have like my character C is now the number 4. And so the bit pattern is a bunch of zeros and then 1, 0, 0. OK, so we have the number 4. And then if I shift this to the right, C right shift equals, let's say 1, right? So this is the 2 squared column. And I'm just going to move all the bits to the right by 1. And in this case, I'm not worrying about what I fill with because this leftmost digit is 0. So just for the purposes of this example, I'm not worrying about what the right shift is going to fill with. But here, now I'll have 1 extra 0 on the left. Let's see. Is that the right number? Yeah. OK, so now basically you see that I moved the 1 from the 2 squared column into the 2 to the first column. So now my resulting character down here will equal 2. So we had the effect, basically we threw away bits. If originally C had been like the number 5, I would have had a 1 bit here, and I would have just like thrown it away. So this is like dividing by 2 and truncating, like rounding down the result. OK, so I thought I had one about shifting right in here. Hang on one sec. Yeah, OK. I'm going to come back to this real quick. So when you shift right, as I said earlier, it's arithmetic or logical depending on the signedness of the operand. So we like to ask this kind of question. So, and I'm sure you encountered it in your binary bomb. But basically, if the input number is signed, then when you shift it to the right, you fill with the signed bit on the left. And the reason it's called arithmetic right shift is because it's supposed to work like a division. And so if you're dividing a negative number, you have to preserve its negativity. You have to bring in another signed bit if the sign bit was already on to make sure that, like, for example, -5 divided by 2 should not suddenly become a positive number. So you're going to fill from the left with the sign bit value. If the number is signed but it's positive, then the sign bit is 0, right? So then you won't be able to tell the difference between these two operators. But when it's a negative number, you'll start filling with 1s when you do an arithmetic right shift. And then if your number is unsigned, it's a logical right shift, which is basically just used for tricky, it's not usually used for math, and you'll fill with 0. Yeah?
Is there any way to take a signed integer and force it into a logical right shift?
Yes, we'll do that a lot today. So yeah, the question is there a way to shift a signed number to the right and make sure it's a logical right shift? And basically, you can just tell the compiler that you want the number to be treated as unsigned before you do the shift. So if I have an integer, let's say a, and let's say I want to do a right shift that's logical, what I really want to say is, like, if I just try a right shift equals 2, then the problem is that we're going to fill with the sign bit. So let's say A was like the number, or I don't know, let's see, how would we, if we construct an example, I'm going to show examples where we care about this, but just to show you how it works, if I do this right shift, I'm going to fill with the signed bit because A is signed. So if I want to avoid that, I can just cast A as an unsigned integer before I shift. So I can either say, be really specific and say unsigned int A right shift equals 2, or I think this is allowed, but I think actually I'm going to make sure. I don't know if that would compile, so I'm going to make sure it will. So I'm going to cast A to unsigned int, then right shift it by 2. And then I'm going to store that in A. The cast on the left-hand side was a little sketchy. OK, so yeah, if you want a logical right shift, you can always cast as unsigned before you perform the operation. And then you will fill with zeros on the left, guaranteed. And I guess technically this isn't really defined in the C standard. Like when you shift right, the behavior is not defined in the spec. But for our class, shifting right will always be an arithmetic right shift when it's a signed number. OK, so let's talk about creating a bit mask. And then shifts are going to come back when we use our bit mask. So here we go. So our goal is basically that we have a bit vector, let's call it V. And that just means that it has several different values stored inside the same variable container. And we want to isolate certain bits by turning off the other ones. So we might have like stored several values inside an integer, or we might just be trying to inspect like certain bits. Like when we looked at the floats in lab, we wanted to examine the exponent bits, and so we had to mask off the other bits in the float. So a mask is just an integer, and it's designed so that it has 1 bit everywhere that you want to preserve the original number that you're masking, and it has 0 bits everywhere else. So the reason it works is because, so like if I'm going to write a new bit pattern, I'll just use this one. So, all right, so I have this, let's say I have this bit pattern and I want to find the value of the top 3 bits. So I want to keep these, and or actually to make this a little harder, I'm going to find the value of these bits. So I'll draw a box around them here. So I want to keep these turned on, and I want to turn off all the other bits. So this is a lot like finding the exponent in a float, right? I'm skipping the sign bit, and I'm just isolating these. So basically, what I need to do is design a new number such that I have 0 where I don't care about the original value, and I have 1s where I do. So I'm going to put 3 1s here, and then I'll put 0s elsewhere. So this is like my original number. Let's call it V, because I called it V in my slide. And then here I have my mask on the bottom. OK, so I'm just going to AND these 2 numbers together. And so I'll write an AND sign here. So basically, 0 ANDed with anything else, 0 and 0 or 0 and 1 will become 0, right? Because one of the inputs is false. So all of these areas where the mask is 0 will be turned off. And then where the mask is 1, I'm going to get, let's make this a little more interesting. I'll put a 0 bit here. So where the mask is 1, I'm just going to get the original value of the number, because 1 and 1 is 1, and 0 and 1 is 0. So basically what I've done here is I've kept the bits that I cared about, which is where my mask was 1s, and I've turned off the other bits. So this is really common in low-level programming. Like if you're trying to store a lot of data inside a single data structure, like a small variable, then it's useful. It's also common in like programming microcontrollers, where you don't have very much space. So on this next slide, I basically just have another example of doing the same thing I did on the board. Here, I said let's just select the 3 most significant bits in my character C. So the value of C in binary is written on the top row of the table. And then I construct a mask that's 1s where I care about the value of C. So I just put the 1s here in this case. And then when I AND the mask with the original character, I get this part is black to show that it's turned off. And then I get the original value of C in the bits where the mask was 1. So now I've turned off the other bits in C, right? My result has 0s except for the area of interest. but I still can't, these bits that I isolated are still floating at the top of the number, right? So if I wanted to figure out, like if I wanted to interpret this as a 3-bit number, I have all these zeros to the right of it, so it's going to seem like it's much more valuable than it actually is. So after I isolate the bits, I need to shift them right to interpret their value. So let's do that. I already talked about the caveats of shifting right. Sorry. This doesn't go into the next one. Okay, so our first try, as we talked about earlier, would be we have this character C, right, or character bits that was C ended with the mask. And since I've just called it a character, it's signed by default. So if I just naively say, let's take bits and right shift it by 5, because I want to move these 3 yellow bits to the least significant position in the number, then I'm going to get assigned like an arithmetic right shift. And so I bring in all these ones. And the result is that what I thought I was doing was isolating the number 101, and I actually get the value -3, which isn't what I wanted. So I actually wanted a logical right shift. I want the rest of the numbers on the left to be 0. So to fix it, I just need to cast bits as an unsigned character, or just any unsigned integer type. And then I shift it to the right, and that guarantees that I'm going to fill with 0, regardless of whether the leftmost bit was a 1 before I did the shift. So now the number that I read here is 5, which if I was trying to interpret these yellow bits as a number would make sense, right? 101 should evaluate to 5. Does that make sense? Any questions about designing a mask? Yeah?
Why would we bother doing the mask if we just shift it?
Yeah, this example is kind of weak because I could just shift to the right in the first place, and then it would automatically discard the bits on the right. So in this case, you would probably not use a mask, but if it were a larger, if you wanted the middle bits, you would want to use a mask. And the principle would be the same. So I'm going to show an example where we do that. Let's see, I think. Yeah, so here's an example where we do that. So here the problem, let's say we have, we want to store an image, and we want each pixel in the image to be represented by a 4-byte integer. So let's say our colors are red, green, blue, and alpha channels, where alpha is like how transparent the pixel is. And so just arbitrarily I say I want to store this pixel's color inside a single int, just to save space, for example. So here I've written the format that I want to store it in. The 4 boxes here represent the 4 bytes of an integer. And so in the most significant area of the integer, I want to store the red channel, and then green and blue, and then alpha over here on the right in the least significant channel. So first we want to write a function that will store a color into our vector. So we're going to set a color based on some number. So I'm going to start with my color variable, right? This represents the color of 1 pixel. I have it all zeros. And I wrote this function setRed. It's designed just to set the value of the red channel. So let's see if I can use my mouse here. Yeah, so basically my setRed function takes in the color. Oops, that did not work. Okay, it takes in the color as the first parameter. That's like the color I already have. And then I want to take in the value of red that I'm trying to store. So let's say I want to set the red channel to be the number 0xe0. So what I'm going to do first is I need to take the value of the red channel, and I need to, so like I have my number 0xe0 sitting down here. I want to move it all the way to the left to align with the byte where I want to store it in the integer. So the first thing I do is left shift it 24 places. So basically that's the number of columns it has to traverse before it's in that position. And then I'm going to OR it with the original color variable, which started out as all zeros. And when you OR something together, remember that the output will be true if either of the inputs was true. So basically, OR is useful for setting, like turning on bits in a vector, where I had, this is the number E0, and basically I had all zeros here. So before the OR, I was saying like 0 and 0 becomes 0, 0 and 0 ORed with 1 becomes 1. So basically I'm going to write, the OR has the effect of writing the red channel into the number. And it's, in this case, because the number was 0 to start with, I could have said color plus red left shifted 24, right? But the problem with using addition here is that if my color variable already had some like non-zero values up here where the red is supposed to go, and then I just added my shifted red number to the color, then it might have carried and done some weird stuff, right? So OR is useful for like guaranteeing that the number I'm trying to write here is exactly what I'll end up with after I OR them together. So are there any questions about turning on bits in a vector? Okay, cool. So now we've set a color, and this isn't very useful unless we can get the color back out of the vector. So the next example is reading a color. Let's say I'm starting with a color that already has some non-zero channel data in it. And here I've highlighted in green the value of the green channel, which is the second byte from the left. So let's say the green channel has value EF in hex, and I want to extract whatever number is written there. So I've written my getGreen function that returns an integer because the channel, I could have returned a character as well, but the channel basically stores an integer like brightness value for the green channel. So I'm going to take in the color variable, and first I'm going to mask off the part that's just the green pixel, so the green value of the pixel. So in this case, I can't just shift it to the right, because if I did, like if I start with the color as it's written up there, so what did I write? F0EF001A. Okay, so I might try first just shifting this to the right by, this is 16 bits. And the problem is after I do that, so let's say I just do color, oops, can't spell. Color right shifted by 16, and let's say I just call that green. So if I do this, basically the value of green after the shift will be, and let's say so I'm making two mistakes here, but if I shift this to the right, basically I'm going to keep the whole upper part of the number, right? So I would get something like F0EF. Okay, and that's not what I wanted. I just want the EF part. So what I need to do is make sure the top half of the top half of this result is also turned off. So first I AND with the mask. That turns off everything that's not in the green channel. And then I shift it to the right. And notice that here too, I have to make sure it's unsigned first. So if I just shift the int green, which is signed because I didn't declare it as unsigned, then I'll fill with ones in this case because the most significant bit is turned on before I do the shift. So, or I guess, no, actually, sorry. Here it would be okay, because after I mask, the most significant bit is turned off. But just to be safe, I'm going to cast it as unsigned to make sure that I fill with zeros when I shift right. And this is how I would use my function. So I get an int back, and it just stores, it has the value 0, or EF, and the bits here are shown just in case you want to know what it looks like. Basically, I took the green bits, which were EF, that's what this binary pattern corresponds to. I turned everything else to 0, and then I shifted them to the right. So now they're in a place where I can read the value of the number, and it will actually reflect the value of the green channel. So any questions about getting values out of a bit vector? Okay, cool. So that's all I have for the bitwise operations. We can come back to them if anyone thinks of a question, but I'm going to move on to floats. So the cat is happy about floats. So just to remind you, the float format is 32 bits, so it's the same size as an integer on the Myth machines. And the format is shown in the table here. I've just drawn a float with its three sections labeled. So in the most significant bit, you have the sign of the floating point number. And when the sign bit is 0, the number is positive. And when the sign bit is 1, the number is negative. And then you have what I'm going to call BEXP here, just to remind us that it's the biased exponent. And And this is 8 bits that represents like the exponent that you're going to use for scaling your floating point number. And then the actual meat of the number is in the significand or the mantissa. Those are the same thing. And you have 23 bits of precision with standard floats. So this is just an example bit pattern, but all your actual like interesting part of the number will go over here. Okay, so I'm going to talk about the float types. The main one we care about is the normal floats. So these floats are ones where there's a leading 1 before the significand because the exponent bits are neither 0 nor completely saturated. So this is like this is most floating point numbers that are possible, and it's the one we care the most about in this class because it follows the rules pretty neatly. So basically, as I said, the biased exponent bits, which are stored in this second field, are neither 0 nor saturated, so they're not all 1s or all 0s. And so that means you have valid normal exponents from, like the biased exponent can go from 1 all the way to like all 1s with a 0. So this is basically almost saturated. And when floats are normal, that means that you imagine there's a leading 1 before the significand when you compute their value. And I'll talk about computing the value in a second. So then there's the denormal floats. When people created floats, they were like, well, we can't get really small exponents like this because we always have this leading 1 before the significand. So let's make an exception to the rule. So if all the exponent bits are 0, then we just have an implied leading 0 before the significand. So that allows us to write numbers basically that are much smaller than the standard 1 point something. So we're not going to worry too much about these, but you should know that they exist. And 0 is probably the most common denormal number that you'll encounter, because to write 0 in a float, you need to make sure that basically all the bits are 0. So that's automatically a denormal number. And then there's special floats that we haven't really worried about too much, but to remind you what they are, if the exponent is totally saturated, then you can have infinity or not a number. So infinity happens when the exponent's all 1s and the significand is all 1s. So that means you can have, notice the sign bit can be either way, right? So you can have plus or minus infinity. And then you can have not a number, which basically shows up usually when you have some error in your arithmetic. And so we haven't really worried about not a number. But not a number happens when the exponent is still all 1s, because that signifies that it's a special number. And then the significand is anything except all 1s. So it's just something that's not infinity and has the same exponent bits as infinity. Okay, so let's talk about computing the value of a float from the bit pattern. And this next slide has a lot of text on it, but it's just because I know some people are going to look at the slides only. So if we have we're going to assume the floating point number is normal in this slide. So this is really important, right? The rules are different if you have a denormal number. So let's say our floating point number is normal. That means that we've already checked that the exponent bits are not all 0 or all 1. Okay, so the bias that we're going to apply to the biased exponent bits is 127. And because the number is normal, on this slide, we have an implied leading 1 before the significand. So we're going to use this value equation to figure out the value of the float. And these 3 ways of writing it are totally equivalent. I just wanted to write 3 different ways of looking at the problem in case one of them was more confusing than the others. So first we look at the sign bit, which is the one in the most significant column. And so if the sign bit is turned on, the number is going to be negative, so we'll multiply it by -1. Otherwise, the number is going to be positive. So the sign bit's easy to figure out. But don't forget to look at it, right? Because we want to make sure that we know the sign of the number. And then we have to compute the exponent based on the bias. So the biased exponent bits, which I've called BEXP, are represented by the e's here. We have 8 biased exponent bits. And so we have to subtract this 127 from the exponent bits value before we can exponentiate 2 to the... So this like computes our effective exponent for the number. And then the traditional, like the way you commonly see this written is that you have 1 point SSSSS, where S are the bits in the significand. And this way of writing it shows kind of intuitively what it means. It's like all the significand follows the decimal point. Yeah?
How did you calculate the bias?
Oh, the bias is defined by IEEE 754. Like the bias comes from the floating point creators. But the way you compute the bias, if we wanted to, like when we look at mini float, it's also it's gonna have a different bias. And the way they computed this bias is they took, like there are 8 exponent bits, and so they said we basically want to make sure, since the exponent is an unsigned number, we want to like make sure there's some positive exponents and some negative exponents. So they found like basically halfway up the range of possible exponents. So in an 8-bit number, there are 256 possible values. So here the bias is just defined arbitrarily to be 127, but the idea behind that number is that if we subtract 127 from our positive, like our non-negative number from 0 to 256, then we'll have half of it below 0 and half of it above 0. So this just allows us to write numbers that have negative exponents. So this is something you just memorize for float and for mini float, and it's not going to change. Yeah? For mini float, I don't know, but the bias for mini float is 7. I'm gonna talk about it in a later slide. But the way you like compute the bias in general is that you do 2 to the number of exponent bits minus 1. So here, like we have an 8-bit exponent. So bias is 2 to the 7th. And then I think we subtract 1 from that. Yeah, so here we have, since we have 8 bits, we do 2 to the 7th minus 1. The minus 1 is just like arbitrary. It could have gone either way. But so for mini float, which has a 4-bit exponent, the bias is 2 to the 3rd minus 1. So this is where the 7 comes from. Yeah, so I have another slide on mini floats too. Are there any other questions about this slide? So we are going to do an example, but basically these 3 are equivalent because if I imagine the significand as just an integer, like it's an unsigned integer, then saying the number is 1.SSSSS, right, putting all the integers bits to the right of the decimal place is the same as imagining that we basically add 1 to, this is kind of like shorthand, but it's like I move the significand to the right 23 places. If you really did this, then you would basically just have 0, right? We would discard all the significand, but I'm writing it with this shift just to show that it's like you shifted the significand bits over and added them to the number 1. And the real, like the most correct way to write this would be we take the number 1, which is not moved at all, right? And then we multiply the whole significand by 2 to the negative 23rd, which puts its like last bit all the 23 places to the right of the decimal point. So these 3 equations should say the exact same thing, but it's just different ways of looking at the way we define how the significand comes after the leading one. Okay, so let's compute the value of this float. So this one looks like it's going to be difficult, right? Because we have all the ones in the significand, and it looks like it's going to be really annoying. So first we have to decide whether the floating point number is normal. And so we just look at the exponent bits. Here there are 4 zeros and then 0, 1, 0, 1. So that's not all zeros or all ones, so it's going to be a normal number. Okay, now we have to look at the sign. The sign bit is 1, just because it's on the left here, so that means the number is negative. So our sign term is going to be negative 1. Okay, and now we want to find the actual exponent of the number. So if we just read off the bits, we see it's number 5 because it's 1 plus 4. And so our biased exponent is 5, which means that the real exponent of the floating point number is 5 minus the bias, which is, the bias is 127, so it's going to be negative 122. And so now we have to figure out the value. So normal float means that you have to remember the leading one. It's not going to be written in the significand, but basically right here before the significand bits, we imagine there's a 1. And so our effective significand is all the ones that are already written here, and then an additional 1 before the decimal place. So I've written a binary number that has a fractional part here. And it's just like writing a decimal number that has a fractional part. We can find the values of the columns. So just as a reminder, if I write something like 1.101, then in binary that means this is the 2 to the zeros column, this is the 2 to the negative 1s column, 2 to the negative 2, and 2 to the negative 3. So this number would be 1 plus 1/2 plus 1/8, right? So it's the same as writing a decimal number where each column to the right of the decimal place gets smaller by a factor of 10. In this case, since we're in binary, they get smaller by a factor of 2. So my significand here is basically, I've just rewritten the bits that I found with a leading 1 point. And then the trick here, if I could just say, oh, it's this significand is worth 2 to the 0 plus 2 to the negative 1 plus 2 to the negative 2 plus 2 to the negative 3, I'd be writing for a long time. Or I could notice that if we add just a 1 to the least significant column, then we'll carry all the way up to the left, and we'll end up with the number 2. 10.000 is just the number 10, which equals 2 in decimal. So to do that, basically, I added 1 to the 23rd column to the right of the decimal place. So the amount I added was 2 to the negative 23rd. So now when I want to compute the final value of my number, I know my significand is 2 to the negative 23rd less than the number 2, because to get to this nice number, I added 2 to the negative 23rd. And then I write my exponent term, which is just 2 to the negative 122. Sorry, was I just saying 2 to the negative 122? Sorry. Anyway, and then I multiply by my sign, which is negative 1. So my final value expression here is negative 1 for the sign bit, 2 to my real exponent after I account for the bias, and then the significand is just one term, 1 2 to the negative 23rd less than 2, which was an easy number for me to write. Does that make sense? Are there any questions about finding the value of this float? Yeah?
On the test, would we leave it like that, or do we have to calculate out the number?
We don't expect, you don't have to figure out the value of this number. I mean, you could rewrite this as like 1 over 2 to the 122, but we don't expect you to know what that is. Yeah?
Although if we're on a test, would it be okay for us to write it out in like summation notation?
Yeah, you could also, so yeah, this is like the way to do this without having to write a sum, but you could also say, basically, start with the number 1 and then go all the way 23 places to the right and just use a sum. I think that would be fine. So basically here we would have our same sign, so negative 1 times the same exponent term, 2 to the negative 122. And then we start at the number 1. Let's say we don't do the trick, right? We start with 1 and then we go all the way to 1 over 2 to the 23rd. So we would have a sum here from I equals 0 to 23 of 1 over 2 to the I. So when I is 0, this is just 1, so that's the leading 1 before the significand. And then when I is 1, we have 1/2, so that's the number to the right of the decimal place. And then when we get to I is 23, we have the least significant digit of the float. So these two things are equal. This was just an interesting little trick to make sure that you don't have to write all the ones. Any other questions about this slide? Okay. So let's talk about finding the epsilon of a float. I'm sure you all have fond memories of doing it on your floating point assignment. So epsilon is just the value of the least significant bit in the floating point number. So it's the digit all the way on the right-hand side. Like it's the least significant digit in the significand. So to find the value of epsilon, here I've drawn the significand. On the top, we have the value of the columns. And then on the bottom, we have just some bits that might be there. So I have all zeros and then a 1 in the rightmost column. And this number on the bottom here, where it's all zeros and then a 1, will give us the value of epsilon. Because if epsilon is just defined to be the value of the least significant bit, then I can just write a number where all the other bits are 0 and the rightmost bit is turned on, and then I compute its value. And you have to remember, so if we treat the significand as an integer, or like without considering the exponent term, it's wrapping weirdly, then this column is worth 2 to the negative 23. But we have to remember that the whole floating point number is scaled by the bias term, or by the exponent term. So over on the left here, I have 2 to the biased exponent minus the bias, where the s wrapped down for some reason. So this term is going to scale the value of every column in the significand, including the one on the right. So if I want to compute the value of epsilon here, which is just the value of this yellow digit, then I'm going to multiply my exponent term, which is 2 raised to the biased exponent minus the bias, right? So this is 2 to the effective exponent times 2 to the negative 23rd, because that's the original value of this column before I had an exponent. Yeah? Right. So for mini float, there's only 3 bits in the significand. So this would be 2 to the negative 3. And then the bias would be, I've written bias here, but the bias would be 7 instead of 127. And I have a slide that has that on it too. So. Any other questions about finding epsilon? All right, cool. So yeah, notice that epsilon doesn't depend on the value of the significand, right? Here, this is the exponent of the number, and this is the length of the significand. So this is like defined by the format of the number, mini float or normal float or double. But it doesn't matter what bits are in the significand when I'm trying to find the smallest representable number in the significand. So no matter what the float is, the exponent is just going to depend on the epsilon is just going to depend on the epsilon. Epsilon is just going to depend on the exponent. There we go. It doesn't matter what value is in the float. Okay, so yeah, and I have a slide here on mini float because mini floats pop up when normal floats are too hard to write because they take too long. So a mini float is just like a standard float, except that it all fits into a single byte. It's much easier to work with. The bias is 7 because there are 4 exponent bits, and 2 to the third minus 1 is 7. So this is just using our arbitrary bias formula. And I would just memorize that the bias for mini float is 7 instead of trying to figure out what it is. So the mini float also has a sign bit in the most significant column. It's the same as float. If the sign bit is turned on, then it's negative. Otherwise, it's positive. The biased exponent is 4 bits. So 7 is like halfway up the possible values for the exponent. And then the mantissa just is only 3 bits. So these aren't very precise numbers. But if you want to find the epsilon of a mini float, like we said earlier, you do the same thing with normal float, except now you plug in the bias of 7, and you plug in the length of the significand here, which is now 3 instead of 23. So epsilon still takes the same formula, except we use different values based on the size of the container. So what's the maximum normalized exponent we can have for mini float? What defines a normal exponent first? Like, what are the rules? Yeah. Yeah, so it can't be saturated or all zeros. So if I want to find the maximum exponent, first I'm just going to write the bit pattern. So I'm going to start with the biggest possible number I could fit in 4 bits. And then this isn't normal because it's saturated, so I'm going to turn off the least significant digit. So this is the largest number I can express in the bit pattern for the exponent while keeping it a normal number. And now I want to figure out, so this is the biased exponent, right? So I need to find the value of this number. It's 2 to the, 2 plus 4 plus 8. So we have basically, yes, I'm just going to write this. So 8 plus 4 plus 2 is 14. And then basically, this is before we apply the bias term, right? So here, this is our BEXP, as I've called it on the slides. And then, so our effective exponent, just EXP, is 14 minus 7. So mini floats don't get very big. They go up to 2 to the 7th times 1 point something something. So, and then if you wanted to find the smallest exponent that's still normal, you do the same thing, except now you start with all zeros. You notice that that's not a normal exponent, so I'll do that over here. This works for mini float or normal float. Okay, so we're going to start with all zeros because I want the smallest 4-bit number I could find. And I notice that this is not a normal float. So if I ask for the smallest normal exponent, I'm going to turn this into a 1. And the value of this number is just 1. And then I subtract the bias to get my final exponent. So the exponent is 1 minus 7, so negative 6. So this is the smallest mini float exponent we can have and still keep it like a normal number. And this is the largest one that we can have and still have a normal number. And if it were all ones, then it would be like infinity or not a number, just like a full-size float. All right, so are there any questions about mini float? Cool. Okay, so that's all the slides I have. We can go back and do examples based on what people want to work on. So if you all have a topic that you want to practice more with an example, just yell it out, or I can do an example that I come up with. Yeah?
Are there like, I remember this from the bits assignment, are there like simple expressions to like turn a bit on in like a vector of bits or turn a bit off? It's like and equals or something?
Yeah, so when you want to turn a bit on, you use or, and when we want to turn it off, use and. So if, I'm going to erase this stuff. So the slides kind of showed this, but I'm going to do it again. So if we want to, let's say we want to turn on, let's say we have a character. We want to turn on like just the 5th bit, or make sure the 5th bit is on. So I'm going to draw my character. I'll start with all zeros. And I want to turn on this bit, so the 5th one from the right. So to do this, I'm going to call this char C. So first, I basically just need to construct a number that I can shift over to that position. So I'm just going to use the number 1. So my, basically, I'll call the resulting number D, I guess. So char D. So I'm going to start with the number 1, and I'm going to shift it over here. So if I have 1 here, and I move it to the left 1, 2, 3, 4 places, then I should get the right position. So I'm going to take C or 1 left shifted by 4. So whatever this bit value was before we did the or, when I shift the number 1 to the left by 4 places, it's going to end up right here. And then 0 ORed with 1 is, so let's see, sorry, we'll fill on the right with zeros because left shift fills the right-hand side with 0. Okay, so 0 ORed with 1 is just going to be 1, and all these things are ORed, so they'll just be whatever they were originally. So our result in D is going to be 1, 0, 0, 0, 0. So we turned on this bit, and if this had already been a 1 in C, let's say it was already a 1 and I just wanted to make sure that the 5th bit was turned on, I don't even have to read this bit in order to know that the result is correct because 1 ORed with 1 is still 1. So if I had tried to add this number to this one, then like instead of doing an or, then that would cause me to carry to the left, and so it would end up being kind of a weird result. So instead I'm going to use or just to make sure that even whatever was there originally, it's going to be, the bits where this is 1 will be turned on in the result. And then if I want to turn something off, I use and. So let's say I want to turn off the top 3 bits of the number. So here's my character, just arbitrarily. Okay, so I could shift it to the left 3 places and then shift it to the right 3 places, but then I would have to make sure that it's not signed when I shift it to the right and stuff. So another strategy would be, I want to turn, so I'm turning these off. So another strategy is just to construct a mask where the bits here are 0. So I'm going to put 3 zeros. And then I want to preserve these because I didn't mention anything about this part of the number. So I'll put 1s here. And then when I AND this together, so when ANDing something with 1 doesn't change it because whatever it was, 0 and 1 is 0, 1 and 1 is 1. So the parts where the mask is 1 will be unchanged. And then the parts where the mask is 0 will be turned into zeros. So that basically just deselects bits in our bit vector. So OR is for turning things on, AND is for turning things off. You can think of them as like complements in this case. Yeah?
So in the OR example, since the rest of the bits are zeros, it doesn't affect it. But as far as thinking about like order of operations of bits, like making sure that you shift the 1 over 4 before you OR it with C, like would you usually need parentheses?
Yeah, I guess to be, I think OR binds really loosely, but to be safe, I would put this in parentheses. That's a good point. So the question was about order of operations. Does the shift or the OR happen first? And I don't want to remember the answer to that question. So surrounding that in parentheses, make sure that it works the way we want. Cool. So let's actually do an example where we write a number as a floating point bit pattern, because that wasn't one of the slides. So we're going to use mini float instead of full-size float because we don't want to deal with writing all the digits of a full-size float. Okay, so let's say I just say I want to write the number, let's say it's 0.75 times 2 to the negative 5. So my arbitrary task is to write this as float. And I'm going to say using mini float so that we don't have to write full-size float. Okay, so basically first we have to figure out what 0.75 is in binary because that's going to make our significand. So first what I'm going to do is, actually I need to be careful here because mini float doesn't allow very many exponents. So I'm going to say actually 2 to the negative 1 here, just so that we can make sure the number is normal. But basically, first I'm going to write the number 0.75 in binary. So to do that, I kind of have to just look at it and notice that it's a half plus a quarter. So one way to make that a little easier is I could rewrite it as 3/4. And notice that that's a half plus a quarter. So because I want to know what the power of 2 column values will need to be to make this number. So to write the number 0.75 as a binary number, I would say 0b for binary, and then 0.11. So this is the halves column and the quarters column. So this number is 0.75. And then I want to make sure that I have my exponent in the float. So I have this whole number times 2 to the negative 1. OK. So now, basically, I need to normalize it, right? Because if it can be written as a normal floating point number, then it has to be. So what I'm going to do is just move. I'm going to shift these to the left by 1 place so that there's a leading 1. So, and when I do that, I'm effectively multiplying this number by 2. So to preserve the value, I'm going to subtract 1 from the exponent here. So this number is the same as if I just shift this to the left, then I'm going to have the original exponent times 1/2 because I'm multiplying this by 2 and I want to cancel that part out, and then times 1.1. So we went from 0.75 to 1.5, and to compensate, I multiplied by 1/2 to make sure the value is not changed. And now I can just move this 1/2 into the exponent term. So this is 2 to the negative 2 times 0b 1.1. And the 0b here just means I'm writing binary. So we have like basically 1/4 times 1.5 here. OK, so now I noticed, so this is a normal number, right, because it has a leading 1. And then it's also possible to write it in mini float because the range of valid mini float exponents was basically from -6 to +7. So here we notice this can be written as a mini float, and so I'm just going to say, first we notice it's positive, right? So our float, let's say mini float bits here. First we write the sign bit, so it's a positive number, and then we have to write the exponent, which is -2, in biased format. So normally when I look at the bits of a float, I subtract the bias. And now I know my exponent is -2. So I need to unbias this, like I need to rebias the exponent before I write it down. So I'm going to add 7 to this number. So I get 5, and so then I'm going to write the number 5 here. So we only have 4 exponent bits. So 5 will be 4 plus 1. Okay, so this is we wanted the exponent -2, but we have to write 5 because we're going to subtract 7 from it when we read back the value. And then we want the significand to be basically 1.1 in binary. Oops. Okay, so because this is a normalized float, right, we notice that this isn't all zeros or all ones. We don't have to write the leading 1 from the significand. So I normalize the significand. I'm writing a normal float, so the significand will automatically have an implied leading 1. So all I have to do is write the first thing after the decimal place. So that's 1, and then the rest of the significand is 0 because my number just it doesn't need these bits to be represented. So this basically is positive. This is basically 5 minus 7 gives us our -2. So the 7 was the bias, right? And then here we have, there's an implied leading 1 point and then 1. So that gives us our 1.5. So this is like binary and decimal. So that's kind of messy. So that's basically when we read this back, we can make sure that it looks right. Okay, so any questions about going from decimal into mini float? Yeah.
Is that how hard it would be on the test, or would they say write the number 9 in a float?
So if you wrote the number 9, it won't be so it'll be something that you can figure out from powers of 2. Like I would say, like I don't know what the test is going to look like, but we won't ask you to write a really crazy fraction in binary because that's not the point of the exercise, right? We want you to know about the format of the float and how you would go. Like you have to remember to take care of the bias term, and you remember that the leading 1 is taken care of for you. So it'll be something like, there's not really a general way I can look at this and figure out how to write it as powers of 2 without doing long division. So we don't want you to waste a bunch of time doing long division. So if you had to write the number 9, I would just say that one's not quite as bad as writing a weird fraction because you can basically just add 8 and 1, right? So you can break apart, if it's an integer and you want to write it as a mini float, we can do that if you want to as an exercise. So let's actually write 9 in mini float. Did you all have a question about this before I erase it?
Well, I had a question. It relates to what Travis mentioned, but how to then determine like the smallest value represented in float that would not change that value.
That would not change this one?
Yeah, so basically like epsilon.
Okay, yeah. So let's compute epsilon for this float. So we just look. So epsilon is just the value of the rightmost column, right? And if we want to find out what to add to this that won't make a difference, we just basically add epsilon over 2 or less, like roughly, right? So if we don't worry about rounding too much. So here, the rightmost column has the value 2 to the -3 before we scale it, right? So first, this is the formula for epsilon that I wrote on the slide, but I can just figure it out because this is my 2 to the -1's column. Here's my 2 to the -3's column. So I have 2 to the -3 times whatever the current exponent is scaling it by. So here I have 2 to the 5 minus 7, right? So -2. So this, when I multiply together, the exponents just add. So I get 2 to the -5. And so if I wanted to figure out like what basically the thing that won't make a difference when added to this number is something less than epsilon over 2. So the threshold here would be epsilon over 2 is just 2 to the -1 times 2 to the -5, right? Because dividing by 2 is the same as multiplying by 2 to the -1. So here I get 2 to the negative 6, so which makes sense. So yeah, and for mini float, it'll always be, this column will always be worth 2 to the negative 3, and then you scale by the exponent. And don't forget to subtract the mini float bias before you use the exponent here. Sorry,
Then
here.
The solution would just be 13 in the exponent, or 13 represented binary exponent, then 0 to the next.
The solution, so, do you want to write this as float? Yeah, so if we want to write epsilon over 2 as a new mini float, first we have, yeah, so we have to try to write it as normalized first. And it's going to be possible because we just remember that the minimum mini float exponent is 2 to the negative 6. So basically, this as mini float would be positive, so there's a 0 sign bit. And then I'm going to take the exponent of negative 6 and add 7. So my exponent bits will be 1. And then the significand, since this is a normal number, we already have the implied leading 1. So we don't want anything else. So the significand is just going to be all zeros. So this is how you'd write epsilon over 2 here as a new mini float. And this mini float has its own epsilon, right? But this number, when added to this one, would not be able to change. Like the result would be the same. Yeah?
Is that epsilon over 2 the minimum amount we would have to add to change that epsilon, or the maximum amount we could add where it wouldn't change?
Epsilon over 2, we're not going to worry too much about rounding, but basically, if you add, so let's just say, if you add epsilon over 2, it won't change at all. And then if you add a little bit more than that, anything slightly more than that, it'll change. So the main thing to know is just that epsilon over 2 is like the boundary. And then the way you round when you're on the boundary is not that important. Like it's just a convention. But yeah, in this case, epsilon over 2 is basically the maximum we could add before it would start making a difference. Any other questions about finding epsilon for mini float? Okay, cool. So let's write the number 9 as a mini float, just to practice with writing integers as floats. So I'm going to erase this part now. Okay, so now that the new task is write 9 as mini float. Okay, so the strategy is the same as when we had to write 0.75 times something. First, we need to know how to write the number 9 in binary. So we're going to try to break it down into powers of 2. And this is the same, in this part, it's the same as writing an integer to represent a decimal number, like writing the binary of an integer. So I'm going to start, I know my mini float significand. Let's write the integer 9, and then we can normalize the bits. So let's say I'm going to write 9 in like a character. I'm going to give myself enough bits to write it. So I'll just say I have 8 bits to write the number 9. And then some of these won't end up in the final float. But basically, 9 is just 8 plus 1. So I'm going to turn on the 8 column here. And so this is like my 2 to the thirds column. And then here's 4, 2, and 1. And so 8 plus 1 means we have the number 1001. Okay, so we already noticed, we might notice there's a problem here. I can erase the leading zeros because the mini float only has 3, actually, no, we're okay. So as long as we can write this as a normal number, then we'll fill exactly the whole significand of the mini float with the 001. So I'm going to normalize this number, which means I need to write 1 point something. So if I normalize this from its integer form, to get this to be the ones column, I'm going to write 1.001. And then I need to compensate for the amount I just divided this number. So I shifted it to the right 3 places to make this happen. So I'm going to multiply by 2 to the third to undo the change. So this number is equal to my original number 9. Okay, so now it's normalized. And basically by normalizing it, I automatically got the exponent that I need to write the final number. So the steps here will be the same as before. I'm going to write the sign bit, which is 0 because our mini float is positive. And then I need to figure out how to write the number 3 as the biased exponent. So I'm going to add 7 to 3 to get 9. So this biased exponent equals, oh, sorry, did I just do that wrong? 10. Pretend you didn't hear that. So I'm going to add 7 and 3 and get 10. And then to write the number 10 as a 4-bit number, basically I have 8 plus 2 plus 0 and 0. So this is 8 and 2 and then nothing else. So I've written that my biased exponent is 10. So when I subtract the bias of 7, I'm going to get the 3 that I wanted in my original number. And then for the significand, we notice this is a normal number, right? Because when we normalized it, we were still within the valid normal number exponent range for mini float. So my leading one here will automatically be covered by the mini float, and all I need to do is write the part after the decimal place. So this will be 001 here. So this is the same strategy we used when we wrote a fractional number, except when we normalized the number, we ended up shifting it to the right instead of to the left. So our exponent ended up being positive instead of negative. So any questions about this one? Cool. All right, so do we want another mini float example, or do you all want to do another like bit vector example? We good? Anyone have any other questions about previous slides? All right, so I guess we can wrap up a little early unless you all want me to just do another one for fun. But we've covered all the core topics for float. Just remember that the mini float bias is 7, and the normal floating point bias is 127. And then there's the formula for epsilon, where you just you find the value of the least significant digit in the significand, and you scale it by the exponent of the float. And then, yeah, so if you all have any questions after this, feel free to ask on Piazza. Cool. And there's more review sessions tomorrow, so be sure to come to those. Hi.